So they're asking for the product again. Remember, we multiply the r's on the outside, just like we always would. So that gives us 16. We keep our cis, and we do what with the angles? 210 and 330. Remember, when we're multiplying, we add the angles. So that's going to give me 540 degrees, which is not something that I particularly like because it's more than 360, which means I have to go an entire revolution all the way around and then some. So all I'm going to do is take my 540 and get rid of that extra revolution to get to that point, 180 degrees. So this is equivalent to doing 16 cosine of 180 degrees plus 16I sine of 180 degrees. And that then allows us to evaluate those two values, which hopefully you recognize that 180 degrees as a quadrantal angle of -1, 0, which means our radius is a length of 1. And so when evaluating this, I get 16 over 1 times, remember cosine is always the x over the r, so that would give me a -1. And then 16I times the sine is always the y over the r. So in this case, that would give me a 0, which means we will actually come up with an answer. Even though we can still say it has 0 i's, we won't usually write it and simply just give them the real part of -16. If you want to put it in complex form, you'd have to do this, which I'd rather not say I have nothing of something because it's just more work than it's worth. All right. So again, be very careful with these. Really, really simple stuff. Much easier than some of the things we did earlier on. It's just applying some of those reference angles and or quadrantal angles like we had in this one. So here we go. We're going to take the 12 over 6, which we know is 2. We will keep the cis. Only thing you got to be careful of is the angles. That's the one thing that doesn't kind of hold true to all of this, which is why I took the time to actually derive the product, not the quotient theorem. So in this case, we're going to have to take the top and subtract the bottom, which right away you should know that that's definitely a negative. And so when I find the difference between 310 and 70, I'm going to subtract 10 and then 60, because I know that together gives me 300, and then I'll subtract the 60 off of that, which gives me 240. And that's how I can do it in my head pretty quickly. Now, don't forget, it is negative, which means when we go to see where this is located at, to figure out what things are going to be positive and negative, when we expand it out, I have to go in the negative direction, which means downwards first. And I'm going to have to go 240 degrees, which means 180 plus how much more? Hopefully you said 60. So I know I'm going to be using a reference angle of 60, and careful, I'm going to be in quadrant 2, not 3, because of the negative. So expanding this out, then I will evaluate my trig functions. So I will have 2 times that plus 2i times that. And I know I'm in quadrant 2 because of the negative, which means this is going to be negative something, and this is going to be positive something. And since we're dealing with a reference angle of 60, we know the cosine of 60 is 1/2, and the sine, therefore, is the other in the 30, 60, 90, root 3 over 2. And simplifying that, pretty simple. Only when you're multiplying can you cancel, remember. And that would give me a -1. Everything's positive over here, so positive. Multiplying those, the 2's would cancel there, and I'd get, don't lose your eye, root 3. That's it, my friends. Pretty simple. The product and the quotient theorem. Just be careful with the angles. And then when you go to evaluate, knowing your reference angles, and particularly the quadrant and whether they're positive or negative. All right. Moving on to example 3. As we know, we will not always be given things that we can use very simply. So whether they look pretty nasty at the beginning or it turns out at the end, we don't have reference angles in any one of our 4 quadrants, then obviously we're going to have to use the calculator. And of course, they want it in rectangular form. So giving you one example of each, this is obviously a product rule. So I'm going to take the 2.8 and the 5.4 and multiply those. And then I will take the cis, and since I'm multiplying, I will add the angles. And that yields, now that I have that, I will expand and evaluate. And because 113 degrees is definitely not something that I know a reference angle of, I will then have to take that and use my calculator to evaluate. So I'll do that real quick, show you the final answer so that you can check your calculator work as well. And if you got that, excellent, very good. Don't forget, make sure your answer makes sense. Because we had 113 degrees as our angle of rotation with a radius length of walking out a little over 15 units, then that would obviously put me past the 90, but not to the 180 to give me something over here in quadrant 2, which means I would have had to have gone both left and then up to get to that point. So my answer does seem to make sense. And of course, we know that our X and Y, or A and B, should be less than our R, and both of these are. Okay, so let's try one that has radian measure now and a quotient instead. So again, pretty nasty numbers. Let's make sure that we know how to do that very quickly. First, dividing the R's, and then remember what we do with the angles, whether they write it out as cosine theta plus I sine theta or cis. Hopefully you know that you would be subtracting those angles. So taking that and dividing actually works out really nice. It gives me a 3. And then I'm going to write it in the condensed form for now of cis. And I'm going to have to take the top and subtract the bottom. Which, remember, we only know how to add and subtract like things. Right now, these are cut into sixths and fourths, which are different. So remember also that the only thing that I can ever multiply by that will not change its value, but maybe the look of it, is a fancy or funny looking 1. So between 6 and 4, you can always multiply by each other to get the common denominator, but I'd rather just get the least common denominator, and I know 4 and 6 can multiply to be 12. So I'll multiply by a 2 over 2 to get 10 pi over 12 here, and then 3 pi over 12 here to give me a total of 7 pi over 12. So that would be the next part that would go in there. Now, if you don't like that, you don't like the fact that they are in radian measurement, you could have either at the very beginning changed those out, which you know, hopefully, that this is a 30-degree reference angle, and we're multiplying it times 5, so that's 150. And then minus pi over 4, you also should see a reference angle of 45. So you know right then and there that that is equal to 105 degrees. And you could have just written that in there. Or you could have taken this and done what we did at the very beginning of this class and changed from radian or degree measure in order for our angles to be used. So remember, a funny looking one that you also can use is 180 degrees over pi. And that would have canceled those out. And then 12 goes into 18 once with 6 left over, bring down our 0. 12 goes in that 5 times. So we'd have to do 15 times 7, which I already know 7 times 10 is 70. And then 7 times 5 is 35, which gives me my 105 degrees. So changing it at the very beginning is much, much easier. But either way, you have to then take this, whether you keep it in radian measure and change your calculator to radians, or you change it to degrees and then use that, your call. 3 cosine of 105 degrees plus 3I sine of 105 degrees. And again, 105 is not one of those that we know right off the top of our head, no reference angle, so that means calculator. And then that would give us a final answer of, which again, hopefully we can see makes sense. Because of our 105 degree angle, we knew that we are just past the 90, So we're definitely in this quadrant, which to get there, we would have had to have gone left and then up. All very close actually, but all less than our radius of 3. And why was it so close? Well, remember we were at 105 degrees and straight up and down right there would have been 3. So we were a little bit past, which is why we were just a little bit less. So again, very simple. That's basically it for this section, but I wanted to give you a little thought of why we're doing it, like we talked about at the very beginning, in this polar form, when all the answers they've wanted have been in that regular rectangular form. So this is kind of like what I like to call a segue example. All right. Don't know if you guys have ever seen that term spelled out, but a segue to the next video in section we call de Moivre's theorem. So de Moivre was actually a French mathematician. I know it doesn't really sound like it's spelled, but the French mathematician that came up with this, uh, pretty smart, not too ingenious though. If we had some time to actually go through this and think about it, this is what he did. He said, well, what if we had these polar forms, but instead of multiplying by two different r's or two different thetas, what if we had it raised to the power? So we're going to look at just a couple of these examples because if I wrote this out, then that's what I would have. Now I wrote it in two different colors just so that you could see this is the exact same thing that we were doing previously, but instead of them being two different r's or two different thetas, now they're the same. So we're looking for a shortcut. We're looking for a reason to not have to do a lot of work because when we raise it to the third, the fourth, the fifth, that can get a little labor intensive. Okay. So I know that I multiply the outsides when we're finding the product, just like we did in the previous couple of examples. So, but this time I have the same two r's and we write r times r in a simpler form as r squared. Then keeping the cis like we talked about, I will then take theta. And remember when we're multiplying, we're going to add those. So a theta plus theta. We also can rewrite in a simpler form as, so you can see very simply, that's what we end up with any r or any angle theta. And of course, we could then evaluate and do all that. And some of you are already probably looking at that 2 theta and licking your chops or counting your blessings. Oh no, double angle formulas. Don't worry about that just yet, all right? But let's take a look at what if we had r cis theta to the third. What would that entail? Well, remember, that would mean we would have r cis theta times itself 3 times. By definition, that's what any power represents. Now, the cool thing is we already did what it squared is. We already know what those two are. It's this. So I can take these two things and I can rewrite it like we did previously as r squared cis of 2 theta. And just multiply that with this third. And now I can treat it just like I had in all the other ones and multiply the radii, which I know r squared times another r would give me r to the third. Cis, take the angles, and remember when we're multiplying, we add them. So 2 thetas plus another 1 theta would give me 3 theta. And so hopefully you are at the point that de Moivre was, where he was like, that seems very simple. And it seems like there's a pattern to whenever we have an r cis theta to a power. What do we do with that power? What is my end result? So what if I asked you to say r cis theta and raise that to the fourth? Can you guys tell me what the pattern is and what the answer would be? And if you need to pause it at this point and actually think about it, slow down, go back, rewind, and take a look at this again and how we came up with it, that's fine. But at this point, hopefully you saw that what happened when we squared it, well, we ended up getting the r squared. When we cubed it, we ended up getting the r cubed. So that seems pretty easy. But what about the angles? Remember, we're going to have this thing times itself, whatever the exponent is, that many times. And what we said we would do when we're multiplying is add the angles. And so when I have an x plus an x plus an x plus an x, well, then I can say I have x 4 times. And so same thing with this theta. Whenever I have r squared, notice I had 2 thetas. Or when I had my r cis theta cubed, I had 1, 2, 3. So 3 thetas when I added them up. So what could you then say would I get when I have r cis theta to the 4th, 5th, or in general, any power? Because if it's any power, then that means we've found that this applies to complex polar form that's raised to the nth. And so hopefully you came up with r to the 4th. Cis, what would the angle be? 4 theta. Very good. And then r to the 5th, cis 5 theta. And so in general, we're going to say that this would be r to whatever the power is, any power, times cis, and we would have that theta added together n times. And that, my friends, is what is called de Moivre's theorem. And we will see some of the applications of that in the next video, next section. All right. So that's it. Multiplying and dividing with these, what are called polar or trig complex numbers. Pretty simple. Just be careful with some of the little nuances like addition and subtraction of the angles for multiplying and dividing, as well as the signs, depending on what quadrant you're in. That's all I got for you. Alan, signing off.